So we've learned how to build classification models, and those classifiers that we generate from those are going to predict classes of values. In a binary classifier, it's just a 1 or a 0, true and a false. And when we built those classifiers, we generally held back some test data so that when we got our results from the classifier, we could compare the predicted value with the actual value that's in the test data. And that is something we can use to measure how effective our model is. You might think one way to do that would be to simply look at the results and just go through and count up the number of times that we got it right, and then divide that by the total number of observations, and that should give us an accuracy rate. So you can see our accuracy there is 70%. Well, that seems like it might be pretty good, but actually accuracy is not a very good way of measuring the effectiveness of a classification model. And I'll show you why. Now imagine that I had that same test set, but instead of designing a model that carefully looked at the features and tried to predict whether a flight would be late or not, I just got lazy and built a model that always predicts 0. What would that look like? Well, here's the output we get from that. And again, if I go through and I just tabulate all the ones I got right and count those up, I actually get a success rate this time of 80%. So it looks like this is a really good model. But actually, it's just always outputting a 0. So the reason that it's accurate is because most flights are on time. So there are more zeros than ones. And so by predicting 0 all the time, I get, by and large, most guesses right. But it doesn't actually help me if what I want to do is identify flights that are going to be delayed. It's never predicting a delay for a flight. So there has to be a better way of measuring the effectiveness of the model. And there is. It's called a confusion matrix. Now, before you get confused about that, let's take a look at what a confusion matrix actually is. What we do is we plot the predicted label on one axis and the actual label on the other. And the values that are possible in a binary classification algorithm are 1 or 0 for predicted and for actual. And what I do is I look at the number of times when I predicted a 1 or a positive, and the number of times that it was actually a 1. And that's what I call my true positive rate. So I predicted positive, and it was positive. So the next thing I might do is look at the number of times I predicted a 0 or I predicted negative, but actually it was a 1, it was positive. And in that case, I call those my false negatives. And I might also look at the number of times that I predicted a 1, but actually it was a 0. So I predicted positive, but it was negative. So those are my false positives. And then you've probably guessed the final one. The number of times that I predict a negative, and it is a negative, is my true negative. So I've got these different metrics that I can use to look at the way that I've predicted the data and judge how well the model is performing. Now, it's worth at this point mentioning that when you have a classification model, it doesn't actually predict a pure 1 or 0, or at least it very rarely does that. Typically, a classification model is going to predict some sort of value. And that value is going to be, between 0 and 1, let's say, but it might be something like 0.3 or 0.6 or 0.51. And what we do is we use a threshold to decide whether we should round that up or down to a 1 or a 0. So if I get a value of 0.51, my threshold might be at 0.5, and I might say, well, it's greater than half, it's nearer to 1 than it is to 0, so we'll call that 1. Now, if I've got a whole bunch of false positives when I look at my actual results, that might be because that threshold's in the wrong place. And sometimes you want to err on the side of caution. You want to err one way or the other deliberately. So if, for example, you were building a classification model where you were predicting whether people needed a particularly expensive medical procedure, you might not want a large number of false positives because that's going to cost a lot of money to treat these people and cause a lot of inconvenience for them unnecessarily. So you might want to tune your model so that it doesn't have a lot of false positives by changing where that threshold value is. So that's something that's worth bearing in mind when you're looking at your classification model and evaluating it. Using these metrics in the confusion matrix can really help you make that judgment call. So let's look at what that looks like for our actual data. Here's my predicted and actual values that we saw earlier on. And if I plot the confusion matrix for that, I can see that I've got 1 true positive there. I've got 1 where I predicted 0, but it was actually a 1, so that's a false negative. I've got 2 where I predicted a 1, but it was actually a 0, so those are my false positives. And I've got 6 where I predicted 0, and it was actually a 0, so those are my true negatives. So I can see that I'm leaning towards predicting on the negative side. On the negative side, it looks pretty good. I've got a lot of true negatives. but my number for true positives is actually the same as my number for uh, false negatives. So I'm not really doing very well in predicting positives. Now, what I can do with these other metrics that I've got, these metrics in the confusion matrix, is I can go and calculate some other things that will help me judge even more closely how well the model is performing. So I can take those values, and first of all, I can calculate something called precision. And precision is defined as the number of true positives divided by the number of false positives plus the number of true positives. In other words, it's the number of times that I predicted positive compared to the number of times that it was actually positive. And what I get from that in this case is a value of around 33%, which is not particularly high. So you can see that it's not really doing very well on predicting those. And another measure that I can use is recall. And in the recall measure, it's the number of true positives divided by the number of true positives and false negatives. In other words, the number of actual positive values compared to the number of times I predicted a positive value. And in this case, again, it's not particularly high, it's at 50%. So by using these more advanced metrics, rather than a simple accuracy measure, I'm getting a much better picture of how well that model is performing and what adjustments I might need to make to the threshold and so on. Now, if I make adjustments to the threshold, and I can run simulations against the model to find this out, what I can start to do is to plot, based on the threshold I'm using, the number of false positives against the number of true positives. So that true positive rate against my false positive rate. Now, if I don't have a model at all, if I'm just simply predicting binary classification values just by randomly guessing, I can probably expect on average to guess right about half the time. There's only two possible values, so the guess is probably about 50%. So that diagonal line represents what would happen if I just guessed, if I didn't have a model. When I plot my true positive and my false positive rate for my model, I actually end up with a curve that looks like this. We call it a ROC curve, a received operator characteristic curve. And that ROC curve shows me, based on these different thresholds, what true positive and false positive rates I can expect. And a perfect curve would go all the way up the left and all the way along the top. And that would show me that I'm pretty much always getting it right. Usually it looks something like this, where it's slightly better than a random guess, but it's maybe not absolutely perfect. And the thing that I use to measure how effective the model is, the actual measurement that I use, is the area underneath that curve. We call it the AUC, or the area under the curve. And that's a measure that we can use as a pretty good comparison for different models that I've built to help me which one is predicting best and choose that one as the one that I want to use in production.